All right, today what we're going to be looking at is earth fields. So that is on the third page of your blue notes is what we're going to be going over. All right, so let's say I have a simple map here, and on my map I have two cities. I have city A and city B. And city A and city B are connected by two roads. Road 1 and Road 2. Now, on a typical road map, it pretty much just has distances on it. And if I was trying to figure out what would be the simplest route to take from A to B, I'd probably say Road 1, because Road 1 is shorter than Road 2 is. However, let's say I was riding a bicycle from A to B. I might be concerned about something other than just the distance, because one might be shorter on a map, but there might be a big giant hill right there. And maybe that's why Road 2 exists, is Road 2 is nice and flat and is designed to go around the hill. So if I was riding a bicycle, what I might find helpful is, besides having distances on a map, I might want to know elevations, so I can see where the hills are. Or I might be interested in temperatures. Maybe it's colder up here and warmer down there, and I'd rather take the warmer route. Or amount of precipitation. Maybe it's raining up here and not raining down there. So the point being is, there's a lot of other information than besides just distances that you could put on a map. And when I plot other information on a map, like elevation, like temperature and stuff like that, what I'm creating is a field, or a field map. So a field, an area that has a measurable value of a given property at every point. So basically I'm measuring some other quantity, temperature, pressure, something like that, and putting it on a map besides just the distances. All right. Now there's two different types of fields. We have something called a scalar field and a vector field. A vector field is when I'm measuring something that has magnitude and direction. So the best example of that is wind. Because when you describe a wind, you normally say the wind's going, 10 miles an hour from the north, or 15 knots from the east, something like that. It has a magnitude, 15 miles an hour, and a direction, east. Right? Normally you don't just say the wind outside's 5 miles an hour. You usually give the compass direction with it. So that's what a vector field is. It has a magnitude, like a speed, and a direction. A scalar field is something that has magnitude only. So an example of that is temperature. If it's 32 degrees Celsius out, I don't say 32 degrees Celsius up or 32 degrees Celsius left. It's just 32 degrees. So it's just a magnitude. Something like temperature does not have a direction with it. All right, so scalar fields just have a magnitude, vector fields have a magnitude and a direction. All right. So going to my map here, I'll get rid of the roads for right now. But let's say that I put in some temperature values on the map. So I had a whole bunch of observers all over the place, and they gave me a bunch of temperature readings, and these are the temperature readings that they had. All right, so let's say those are the temperature readings that I have on this map. All right. Now, right now, if I wanted to find where the highest temperature was or where the lowest temperature was, what I'd have to do is I'd have to scan through all these numbers and look for, where there's the highest temperature, lowest temperature. And on this one, there's not that many numbers on there, so it wouldn't take that long. But maybe imagine like a map of North America where it had every temperature for a community with 100 people or more. There'd be thousands of data points on there. So just scanning through the numbers is not a very efficient way to look at that data. So what we use on field maps to make more efficiently look at the data is we use something called isolines. So isolines are lines connecting points of equal value. Right. It makes looking at field data a lot easier. All right, so how I would go about drawing isolines on a map like this. First off, I need to know what my isoline interval or contour interval is. That's how frequently I'm going to draw the line. So let's say on this map I use an interval of 5. So what that means is I'm going to draw a line for multiples of 5, like 5, 10, 15, 20, and so forth. So I'm going to draw a line to the interval of 5. So when I draw isolines, it's usually easiest to either find the lowest value in the map and work up, or the highest value and work down. I'm going to do the lowest value and work up. So looking at my map, I see the lowest value is this 21 right there. So if I'm going from 21, working my way up, the first multiple of 5 I'm going to encounter is 25. So I'm going to draw a 25 line. So looking on my map, I'm going to start, I look and I see a 25 line right there. All right? So I'm going to draw a line through the 25. And what I want to do is I want to make a line that every value on that line is exactly 25. All right? So I see a 25 right there. I see a 25 right there. I see a 25 right there. So everything on that line is exactly 25. Now, I can't just have my lines stop in the middle of the map like that. My lines can either do one of two things. In some instances, they might circle up. In other instances, they'll go off the edges of the map. In this case, it's probably better if they go off the sides of the map. So there's my 25 line. There's my 25 ISO line right there. Now notice, everything on that line is exactly 25, but also what that 25 line does is it acts as a dividing line, separating everything that's less than 25 from everything that's greater than 25. So when I draw my 25 line, it separates the less than 25 from the greater than 25. All right, so there's my first ISO line. My second ISO line, going by 5s, would be 30. So I look on here. Here's a 30. Here's a 30 right there. All right. Again, my lines can't just stop in the middle of the map. You either have to circle up or go off the side. So in this case, it makes more sense for it to go off the side. Now I still got to put it off on this over here, and I have to figure out whether I'm going to go that way or that way. But how I know where to put it is, again, my 30 line is going to be a dividing line separating everything that's less than 30 and greater than 30. So if there's 27 right there and there's 32 right there, my 30 line is going to go between them like that. So notice, everything on that is exactly 30, not like a 32 or a 33, exactly 30. I go off the sides of the map. Everything on one side is less than 30. Everything on the other side is greater than 30. All right? And also notice, my lines run somewhat parallel to each other. If you're ever drawing isolines, and you drew them and you had something like that where they crisscrossed, you automatically know you made a mistake. Isolines can never crisscross. The reason why they can't, well, look at this. Here's a 25 line. Here's a 30 line. So everything on this line is 25. Everything on this line is 30. If they crisscross right there, what would be the value of that point, 25 or 30? So like one line, well, one point can't have two different values at the same time. So ISO lines can never crisscross. If they crisscross, you automatically know you did something wrong. They, for the most part, run parallel to each other. Okay. So anyway, there's my 30 line. All right, next one I'm going to draw would be 35. So I look on here. I only see 135 on there, but I can still draw my 35 line, because if there's 33 and 37, I know 35 goes between the two like that. If there's 34 and 36, I know 35 goes between them. 34 and 37, I know 35 goes between them. 33 and 38, I know 35 goes between them. And they go off the side of the map like that. So anything on that line is exactly 35. Everything on one side is greater than 35. Everything on the other side is less than 35. All right, the next one I'm going to draw is my 40 line. And I look on my map and I don't see any values that are exactly 40, none whatsoever. And you might be like, can't draw a 40 line then? Well, that's not the case. I can draw a 40 line. So what I'm going to do is, again, if that's 39 and that's 41, I know 40 has to be in there someplace. So I could draw my line right there. 39 and 41, 40 is going to be between those numbers. 37 and 42, I know 40 is going to be between those numbers. 38 and 43, I know 40 is going to go between those numbers. And they just kind of go off like that. So even though I don't see any values on here that are labeled 40, I can still draw my 40 line, because the 40 line is going to separate everything that's greater than 40 from everything less than 40. All right? So that's how you go about drawing isolines on field maps. All right. Now, what field maps like this are quite often used for is to calculate the gradients between 2 points. What gradient basically describes, if this was elevation, what gradient would basically describe is like how steep the land is. It's how much change takes place over a distance. It doesn't have to be elevations. If you're dealing with elevations, it's basically telling you if you have a big gradient, it means the land's very steep. If you got a small gradient, it means the land's flat. But there's temperature gradients or pressure gradients and stuff like that too. It's just measuring how much change takes place over a certain distance. Now, in your reference tables, right here, you have a formula for gradient, change in field value divided by distance. So it's this number, this thing right here. All right. So let's say I have a map over here, and what I want to do is I wanted to calculate the gradient between point A and point B. Now, how I go about calculating the gradient, all right, so change in field value. All right, so I just showed you how to draw isolines, so you know what isolines are. So if I look, point A is on the 15 isoline. So that means that A has a value of 15. Right? And then B is on the 45 isoline. Now it tells you right here the map is degrees Celsius, so these are temperature readings. Right? So A's got a value of 15, B's got a value of 45. Here's the scale of the map right there. And what I want to do is calculate the gradient between them. So how I go about doing that, the top part of my formula right here is change in field value. That's how much of a, in this case, would be how much of a change in temperature do I experience as I go from A to B. So to do that, again, B has a value of 45 degrees Celsius. So I go 45 degrees Celsius on top, minus A's got a value of 15 degrees Celsius. So 45 minus 15 tells me how much the temperature changes as I go from point A to point B. On the bottom is the distance, or how far apart they are. All right. So here's a scale for my map right there. So I could use the edge of a piece of paper and come over here and mark a little dot where A is, mark a little dot where B is. I could come down to my scale here and I can see that the 2 points are 3 meters apart. 3 meters apart. So that's how far apart they are. Now I could simplify my formula here. So I go 45 minus 15, there is a 30 Celsius change in temperature, and the temperature changed 30 degrees over 3 meters. So my gradient, 30 divided by 3, my gradient would be 3 degrees Celsius per meter. So what that means is, on average, every meter I go this way, on average, the temperature changes 10 degrees. That's what that means. Now, just like with our rate of change problems that we did earlier, with gradient, units are very, very important, but there's not a set unit for gradient. Your units are going to be dependent on the problem. So in this case, my units were degrees Celsius and meters, so my final thing was degrees Celsius per meter. But in another problem might be how many feet per mile, or how many degrees Fahrenheit per yard, or things like that. So your final units are going to be dependent on the problem. And this was just one example of a gradient problem. Probably the most common gradient problems are ones that are similar to this, where you have like a isoline map, or a contour map's another word for that, and you have to get the values and distances off a map like that and figure it out. But it's not the only way. You can also have gradient problems where it's a word problem, and you have to pick out the data in a paragraph and stuff like that too. So this is just one example of a gradient problem. All right. Now, later on, we're going to look at topographic maps, which is a very specific type of isoline map, called topographic maps or contour maps. So we're going to spend like another day, another lesson dealing with this. But just for right now, I'll point out a few things with these. Topographic maps, the isolines represent elevations. Isolines, the generic term, that could be anything. It's like an isotherm would be isoline that deals with temperature. Isobars, isoline deals with pressure. So isolines is a generic term. But with topographic maps or contour maps, what the lines represent is elevation. And on them, if the lines are really close together, what that means is the line's very steep or it has a big gradient. If the lines are far apart, that means that the area is pretty flat or has a small gradient. With the stream, wherever there's V's in the contour lines, that shows you where a stream is. A stream goes down the middle of the V's, and I can tell what direction the stream is flowing because the little V's always point upstream. So if the V's are pointing that way, it means the water's flowing that way. And this one here, where the line has a bunch of these little, what they call hash marks on them, that's a depression contour. That means that instead of counting up and counting down, so you might have those if you're dealing with like a sinkhole or a crater or something like that. But we're going to spend a lot more time talking about this stuff on another occasion. So today, the main thing you want to get out of was what a field map was, what isolines were, and gradient. Now, one last thing I want to mention here is this right here, a field map, where I drew isolines. This is a two-dimensional diagram, basically. So let's say, like in the classroom, if I gave everyone a thermometer and they were sitting at their desk, they might take temperature readings at one level like that, and then we could draw an isoline. But let's say that I gave everyone a thermometer, and instead of just taking a temperature at their desk level, what they did was they bent over and took a temperature down near the ground, then took a temperature at desk level, then they took a temperature this high, then they took a temperature that high, and then they got up on their desk and they took a temperature way up there. So instead of just having one level of temperatures, I had a room where I had a bunch of temperatures at a bunch of different levels. All right. In that case, what I could do is, instead of drawing a map that has isolines, what I could do is make a diagram that has isosurfaces. And what that would look like. All right, so Okay, so let's say that's a classroom, all right? And I had people take a bunch of temperature readings around the room, not just at one level, but at a bunch of different levels. What I could do is I could make an isosurface. What an isosurface would be is something that looks like all right, so that might be like the 25 degrees Celsius surface or 25 degrees Celsius layer. So that's what an isosurface is, a surface with all points having the same value. So it represents a diagram in like 3 dimensions. And then there might be another one that goes like, you know, that might be like the 20 degrees Celsius isosurface. So if that one's 25 and that one's 20, a spot right here would be probably have like a temperature of 23 or something like that. Now for this class, you're going to be responsible for having to draw isolines. That's something you have to be able to do. You're going to have to know how to calculate gradient. Isosurfaces, you probably never actually have to draw one of these. On a test or something, what you might get is a question along the lines of, you know, if there was at point X in that diagram, what could the temperature be at point X? Well, if it's between the 20 and the 25 surfaces, it'd probably be like 23 or something like that. So that's the kind of question you might get with isosurfaces. So you need to know what they are and, you know, be able to look at that diagram and kind of figure out the temperatures there. But as far as constructing them, you never have to worry about that. All right. And all right, so that is what you need to know for the 3rd page of Blue Notes. And again, this topographic stuff, map stuff that I just kind of skimmed over, we're going to spend a lot more time on that in another day. All right.